We're going to cover a range of very different use cases around SystemC, which covers a whole multitude of different activities. So we've got systems businesses speaking, we've got EDA companies speaking, telling you what their customers are up to. I'm going to kick off just by giving a short tutorial on the hints and tips on exploiting the latest features of SystemC, the latest cool features of SystemC. The features I'm going to talk about were all introduced back in the last IEEE standard, the 1666-2011 standard, and SystemC 2.3.0. SystemC 2.3.1 is about to be released. Mike will tell you about the very latest features that are soon to emerge in SystemC 2.3.1. However, any new features there aren't actually part of the IEEE standard yet. They're experimental features that may find their way into the standard later. Anyway, Mike will tell you more about that later. I'm going to tell you about cool features in the current standard. And what I've tried to do is to pick the most useful and coolest features that got introduced in the latest round of SystemC standardization that I suspect not everybody is using yet, or not everybody is using to the full, and just introduce you to those. So starting with SC Vector. So SC Vector came into the latest SystemC standard. It's actually extremely easy to use, which is the nice thing about it. It effectively just allows you to create arrays of things in SystemC. And you might wonder why you'd need to create an array of something in SystemC, because you could just use a C array, or you could use an STL vector. But the point about the SC vector is, firstly, it is an SC object. So if you use an SC vector, you have an SC object. You can use all of the features of SC objects. And secondly, SC vectors understand all about ports, so that you can use the SC vector kind of vector as a port and use it to bind things together. So let's see how that works. So over in the top right-hand corner, we're just creating a vector of ports. We've got an SC vector port vec. And that port vec now can just be used like an array. When you declare a port vec object, it hasn't yet got a size. You give it a size through its constructor, or subsequently after constructing it by calling its init method. So over here we're naming our port vector and saying this particular vector has 4 elements. And from that point it works just like an array of ports. We can do the same trick with signals or other channels. So here we've got sigvec, which is just a vector of signals. And down here in the constructor we're naming our sigvec and giving it a size to say we've got a vector of 4 signals. So now we've got a vector of 4 signals, we've got a vector of ports, and the really cool thing, we can bind our port vector to our signal vector with a single line of code. So we've got C arrow port vec dot bind sigvec. So this is a thing that you couldn't do had you explicitly declared C arrays or STL vectors. We've bound our vector of ports to a vector of signals in a straightforward way. We can also create vectors of modules. In fact, you can create a vector of anything that's derived from SC object, so including just a raw SC object. So in this case, we've made a vector of child modules and a vector of signals. So child is a SystemC module. We've got an SC vector of child modules, so effectively an array or vector of modules. And you can choose whether to make a vector of pointers or a vector of objects. In this case, we've actually got a vector of objects rather than a vector of pointers to objects. And it just works fine. It all works quite transparently. You don't have to think about it. You could just use this as if you're creating an STL vector, an STD vector. So then down here inside the constructor, we've named our new vectors. And we're separately, programmatically initializing the vectors to say how big they are, 4 children and 4 signals in this case. And then we've got a for loop to go off and actually bind all the ports. This slide is just highlighting technically what these SC vectors look like with a bit of UML on the right-hand side here. The bottom line is you just use them like arrays. So having declared your vector and sized it in its constructor, it's then got a size method, so we can see how many elements there are in the array. We can use the subscript operator, just like it was a C array or STL vector, to pick individual bits out of that vector. And we can use STL style iterators to iterate through our vector. So here we've declared ourselves an iterator, STL style, and then we're using that iterator to control the for loop. So basically, you've now got first class objects, which are also SC objects, which behave just like arrays or vectors, and you can use those to create arrays or vectors of all your favorite SystemC things: channels, signals, modules, everything. There's also a lot of flexibility when it comes to binding, and I'm not going to go through all of the available features here, but let's just look at some of the most useful ones. So here we've got on the left-hand side a module with a vector of 8 ports, and on the right-hand side 2 modules, each of which have got vectors of 4 ports. So we could bind the 8 ports on the left to the 2 bunches of 4 ports on the right with 2 bind statements. So we're making the first call to bind, which is going to bind the first 4 of these elements to the 4 elements of the port on the right, and then a second call to bind, which picks up where the first call left off, so we're starting to bind here, and binding the remaining elements to the other 4 ports of the other objects. And there are other features along similar lines. So if you've got an array of modules, and each of those modules has 1 port, you can assemble all those individual ports into a brand new vector and bind that. And there's all sorts of cool stuff that makes it very flexible. Another thing you might want to do is to create a vector of modules where, because you're creating a vector of SystemC modules, you may want to take advantage of the fact that you can have user-defined constructor arguments on your SystemC modules. So here we've got a SystemC module child with a couple of user-defined constructor arguments. We've created an SC vector of our child, and now we've got to figure out a way to actually pass constructor arguments to the objects that sit inside this SC vector. And there's actually a number of different variations on a theme. Here's the simplest one to put on the slide, which is just a global function. So we've got a simple static function here, creator function, which has a fixed prototype, a fixed set of arguments that are built into the standard. And it can then call the constructor of our user-defined module, passing in the actual arguments. If you want to do this stuff, you can look up all the details in the LRM. There's a few different flavors of doing it. But the bottom line is, you can create an SC vector of your own SystemC modules and programmatically pass in all those constructor arguments, so that each instance of your module, even separate instances in the vector, can have their own constructor arguments, which is all good stuff. Or lists. All of the features I'm going to talk about are all features that just make SystemC a better SystemC. So SC vectors are better than just using arrays, because they behave more naturally, more like STL vectors, and they work and play with all the other SystemC elements. Here's another thing that just makes SystemC better: the event or list. So event or lists come into their own wherever you have a module with a parameterized number of ports, and you want to make a process sensitive to that parameterized number of ports. So the classic situation is exactly that. You've got a SystemC module, you've got an arbitrary number of ports, so it could be a multi-port, it could be an array of ports. Now in the current version of SystemC, we'll use an SC vector of ports. So we've got an SC vector of ports. How many ports have we got? Well, we don't know till we actually construct this module. So down here in the constructor, at that point we determine how many ports we've got by passing in the number of ports as a constructor argument. So effectively here we've got a module with a parameterized number of ports. Now suppose we want a SystemC process that's sensitive to all of those ports. Well, as you may know, you've got to write a for loop and start running around and adding ports to the sensitivity list. And the SC event or list allows you to do that in a proper way without any nasty hacks. So we've got an SC event all list object, which is a fully fledged part of the SystemC standard. We're now got a loop which is going through all the elements in this SC vector port using the iterator that I referred to earlier. So the actual number of elements in the port is determined at construction time, right? When we construct this module, we're looping through that port. We are picking up the default event of each port, which is part of the SC interface, and then using this built-in or overridden or overloaded operator to OR each of those elements into our OR list. And then in the body of our SystemC thread, we can wait on the OR list. And if you're going to do this, you've just got to be very careful that once you create your OR list to be sensitive to, you keep this OR list object alive as long as you're waiting for it. So if you create a new event OR list by ORing together all of these events, you wait on it and then you go destroy this object. Bad things will happen. So keep the object alive and in existence while you're waiting on it. Otherwise, it's not going to be good. SC writer policy. This is another improvement on SystemC, part of a long story, but cut a long story short, in the current SystemC standard, for each of your signals, you can specify whether or not you want to allow multiple processes to write to that signal. You can choose to configure things so that the signal can only be written by a single process, which is the default, and that's how it was always meant to be. Or you can now use this second template argument with a value SC many writers, and that allows multiple writers to the same signal. So here we're combining that feature with SC vectors again to create a bundle of interrupts. So here we've got a vector of interrupt wires, so effectively we've got a collection of individual interrupts. And then each of those individual interrupts can have many writers, which means that each individual interrupt signal can be written by one of several processes at different points in time. So here we've got a couple of processes, prop1 and prop2, and at different points in time, alternate processes are writing to bit 0 of this interrupt array. And that's fine because its writers policy is SC many writers. So now we can have signals where the very same signal is written by multiple processes, as long as you don't have multiple processes writing the same signal at the same time. That's an error. But at different points in time, you can have multiple processes writing to the same signal. And that's handy for modeling all sorts of things, including interrupts. Resets. A lot of work went into SystemC 2.3.0 in cleaning up the way resets get handled. So in the previous version of SystemC, clocked processes had this functionality of a reset signal. So you could declare a reset signal for a clocked process, an SCC thread, and only for an SCC thread, in order to define a synchronous reset for a clocked thread. And that was used by those SystemC behavioral synthesis tools that supported clocked threads. Then in the latest round of standardization, we added asynchronous resets to clock threads. So as well as a reset signal, you can also declare an asynchronous reset signal. So the clock thread would have this sort of process style. Normally it's sitting in this inner while loop, waiting on the clock edge. If the reset signal goes active, then on the next clock edge, because the reset is active, we'd start again and come in at the top of the thread. If the asynchronous reset signal goes active, then we'll jump straight to the top of the thread and come in again and perform any reset actions. So asynchronous resets were a significant addition to the functionality of clock threads. Also, the functionality added to clock threads also got added to regular threads. So regular SystemC threads can now also have reset signals and asynchronous reset signals. So this function up the top here could be associated either with our clock thread or with our regular SC thread, and would have extremely similar functionality. There's one slight technical difference. So now the difference between clock threads and SystemC threads, SC threads, well, one difference is that with an SCC thread, you only have one clock, and the clock is the second argument to the macro here. Whereas SC threads, regular SystemC threads, could have any number of clocks or no clocks. An SCC thread has a single clock and only one clock. That's actually an argument. So if you think of it like that, SCC threads are now simply a cut-down version of SC threads. The other slight technical difference is that clock threads don't have their process called during initialization, whereas SystemC threads do have their process called during initialization. That's the only other slight technical difference. That's a nice cleanup. Now it means that clock threads and regular SystemC threads are pretty much the same kind of thing. You can have the same kinds of resets. You can also, which is a bit mind-boggling, but you can also add the same reset, synchronous or asynchronous, to a method process. So here we've got the function associated with our method process, which now looks similar, right? Not identical, because in the case of a thread, we've got an infinite loop inside the function here. In the case of a method, we mustn't have an infinite loop because it's a method process. But otherwise, we could write an analogous coding style. So we could use our method process to describe an RTL process with a synchronous and asynchronous reset, what it would end up looking like. So a little different to threads, because methods and threads are fundamentally different, but you can see there's kind of a unity here. So now it begs the question, what on earth does it mean to have a method process with an asynchronous reset or a synchronous reset? So asynchronous reset. So if the asynchronous reset changes, the function's going to get called, right? Because it's asynchronous. But then you could have achieved exactly the same effect anyway by putting your asynchronous reset in the sensitivity list, right? It's like not a big deal. How about the synchronous reset? What could it mean to have a method process with a synchronous reset? So what's going to happen when the synchronous reset changes value? Nothing, it's a synchronous reset, right? So if it's synchronous, this guy's only going to wake up on the clock. So if the synchronous reset changes value, well, the synchronous reset goes active, the synchronous reset goes active. But nothing happens until the next clock edge. And on the next clock edge, because of the if statement, we'll actually be doing the reset synchronously or asynchronously. So technically, what's the point of having these red lines at the bottom? Well, the only thing they do that's good to know about if you play with this at home, is that they actually reset the sensitivity of the method process. So if you're doing fancy stuff, you're using SystemC method processes, and you're using next trigger to set dynamic sensitivity on the method process. So if you're programming the sensitivity list of your method process, and you then go reset it, the sensitivity list gets reset. So the static sensitivity gets restored. So that's the technicality that you've got to understand if you're going to start adding resets to method processes. Can I think of a really good application for that? No, not really. But at least it makes the API and rules look a lot more tidy and more unified than they were before. So now we've got 3 different ways of setting up resets. So we can set up resets using reset signal as async reset signal is with the process macros. If we're spawning dynamic processes, we've got similar options here, spawn options, to have precisely the same functionality with dynamic processes, so they can also have synchronous resets or asynchronous resets. And we can also use the new process control methods that were added in the current standard to do resets. So if handle is a handle to a process, we can asynchronously reset the process by calling the reset method, or synchronously reset the process by calling sync reset on, sync reset off. So we have asynchronous or synchronous resets, whether we're using the process macros, spawning processes dynamically, or using the new style process control. So for my last trick, finally, let's just talk about the reset and kill process control methods, just to show how they pull things together. So all of the process control methods in current SystemC standard work on handles to processes. Processes have had handles for a long time, but in the current standard, process handles got a lot more powerful and useful. So now anytime you've got a process, you can get a handle to that process. So here we've got two threads, calling and target, and we're grabbing a handle to the target process. T equals SC get current process handle. So here's our target process. It's executing, it's waiting for an event, and we've got a handle to that process T. So the calling process over on the left-hand side can now start manipulating this thing. So let's see what happens. We notify the event gets notified, this guy wakes up, increments Q, spins once around the loop, and waits again. Then we have an asynchronous reset, T.reset. So when T.reset gets called, this guy gets asynchronously reset immediately. So it was sitting here waiting on this event. The reset call comes along, and it immediately jumps out of this function, comes in again at the top, executes Q equals 0, and comes down and waits on the next event. So over here on the left-hand side, all of that exciting stuff was happening in the middle of this call to T.reset. So on the next line of code, when we return from T.reset and check the value of Q, it is 0. By the time we return from the reset call, this process has been messed with, it's jumped out, it's come in again at the top. And so the code inside this process, if you think about it, is actually executing as part of the call stack of this process, right? So all of this reset code is getting executed nested inside the call to T.reset. And the same down the bottom of the slide when we come to kill things off. So we call T.kill. T.kill says, stop this process, terminate it, stop it executing. So the call to T.kill will actually kill this process off prior to the return from T.kill. So by the time we return from T.kill, if we assert T.terminated, it is indeed terminated. So T.terminated tells us whether our process is dead. It is dead. By the time we return from the kill method, the process is dead. So these reset and kill calls really are immediate, like immediate notification. By the time you return from T.reset or T.kill, your process has been killed. So finally, we can see that in action by actually intercepting what's happening by catching an exception. So actually, the calls to reset and kill, T.reset, T.kill, actually throw exceptions over here inside this thread. So we've got an exception being thrown, and we can prove that by catching the exception. And I mean, this isn't just academic. You can actually write a process this way if you want a process that does some housekeeping code when it gets reset or killed, if you were doing some fancy behavioral modeling. So now our thread process was describing its normal behavior here in this try-catch block. If somebody else comes along and interrupts it, kills it, resets it, then we could catch the exception, check what's going on. So if we're in the process of unwinding an exception, SC is unwinding is true, we can even check to see whether we're doing a reset or a kill, and then we could propagate that if we wanted to. So this process could go off and do other stuff. It could go kill other processes. It all gets very mind-boggling, but it all works. And then finally, we rethrow the exception. So that's what's really going on here. So we now got, not only have we unified the three different kinds of process, we've also got a unified way of doing synchronous or asynchronous resets that works across the macros, spawn processes, or using the process control functions. And in each case, an asynchronous reset or an asynchronous kill really is asynchronous. It really does unwind the code here from the call stack of the process that's calling reset or kill.
Welcome everyone. My name is Peter Lohake. I will present use case from the industry representing Ericsson. Unfortunately, Henrik Svensson that was supposed to do this presentation is caught the bug, so he's home. I have two colleagues with me here that will help me cover this. Ericsson radio base station have support for previous and current generation of mobile systems, the 2G, 3G, 4G. and also the different standards, such as GSM, wideband CDMA, CDMA and LTE. So radio base station consists of an antenna, a radio part, which is filters and analog stuff, and the baseband, that is the signal processing part. Typically, a site looks like this with the antennas in a mast and a sort of cabinet containing the radio and baseband units. But coming more and more it's hard to see back there, but there's a lamp post here with a mounted small RBS. This is a much cheaper solution than this one, but also gives a better coverage in an urban environment. A little bit on different type of radio base stations. We have the macro with the cabinet, radio and digital units and the antenna. And main remote where radio part is broken out and put closer to an antenna, and AIR, which stands for antenna integrated radio. So you have the baseband part down here and antenna and radio part. Look inside, climate unit, radio units, digital units, some power and backup, batteries and transmission. But important here, when we talk about system, we always talk about hardware and software combined together, working together. Base station development starts by designing a system on chips. And several system on chips is then combined into a system on board. Could be a radio unit or a digital unit. And a number of such boards are then combined into a system in cabinet. So here we have our current generation of radio base station, RBS 6000. This is a high-level system design process, starting from architecting the system, development and verification of IP blocks, those put together into a chip design, being verified, and creating board design verification, some software tools, and also the application software. And throughout the whole design process, we are using TLM. Some advantages with TLM we see. Primarily, we see an early hardware verification environment up and running. So we will use TLM for verifying our RTL code going into the system on chip. Early software development and system verification. We actually see that with the use of TLM, we can start software development many months earlier than when we have the real hardware in place. Early systems exploration and system dimensioning, other two areas which we see important. So we hope to catch bottlenecks in the architecture at an earlier stage so we can correct them. And then we have some more important advantages, standard and speed of development and so on. This is maybe a busy slide, but trying to illustrate our design flow with TLM. Horizontal, we have the design flow from some reference models through LT models, AT models, RTL, board, and final product. And vertically, we have different areas of use and also different user groups. So one important thing with this is, as I mentioned, early stage soft architects work together with the software to get the best system in place possibly we can. So with an older, so to say, design flow, the software architects created the hardware architect, and when the software was loaded much later on, we could identify bottlenecks and mismatches in the systemization. So a little bit on the history using TLM within Ericsson. So we joined Accelera as associate corporate 2 years ago, but from this year we have now become a corporate level member. Internally we have a bi-weekly TLM steering group where management and the different projects are meeting and discussing issues or other tasks. We'll attend DVCon, for instance. We have been running a number of projects since 2010. We started with a sort of methodology project to see if this with TLM was something that we could take benefit of. We have also run a number of pilot projects for early software development called Helios, and also for architectural exploration called Vulkan 2011. And currently we are running 2 short projects, Ghost for early software development and Atom for primary for hardware verification. And we also have a number of master theses currently. Software development. Today we have a TLM2 LT-based virtual platform for the software development. So we actually have hundreds of software developers using this platform for their development and regression runs. As I mentioned, one goal with this have been starting this software development much earlier than we have the real hardware in place. And we have actually succeeded with this. So I would say more than half a year we have gained in time to market by using TLM and virtual platform. And this is also replacing some legacy in-house and external virtual platforms that have been used before. LT, get the speed. Our models need to be memory or register accurate. That's what the software guys are interested in. We operate both at chip level but also on board level. So our current virtual platform consists of one large SoC, one central processor, and one interconnect FPGA. So we have the whole system over here. Standard debug tools are used. You could get some more visibility with tools from the different EDA vendors. With that, I leave to Jonas.
My name is Jonas Hessmark. I work as a development engineer in virtual platform projects based on TLM2. This is our virtual platform. We support different kind of setups in our virtual platform, and this is the single ASIC configuration. So on this side we have the TLM2 based virtual platform. Before this part existed, we were using what I call here a legacy virtual platform that was not based on TLM2. In order to reuse the software debugger and existing test frameworks, we developed a simulation client that connects to SDP in TLM2. And this simulation client enables this communication between the legacy environment, the debugger features, and our virtual platform. The SDP contains TLM2 based models using the loosely timed timing approach. Some models has to some extent also support for AT or even cycle accuracy. We also support test framework support for streaming data towards the virtual platform. And everything is built an in-house made CCI that controls the communication to and from the simulation client, provides the capability to dynamically create modules, serving for the debug support towards the software debugger, and handles the attribute tree and single-step support from the debugger, any debug features. And this is the configuration for the board level. On this level, we also include other devices on the board, such as the FPGA, peripherals, any IP we might want to bring in, multiple ASICs, just to emulate the real board. In this case, we have a board processor that we emulate in a third-party simulator. So the board processor model contains a different CCI from ours, so we brought it in as with the help of third-party simulator. Also communicating over a TCP/IP socket. Some works on the CCI that we use. So we have created a CPU on the board. We bring it in as an IP, and the IP contains not only the model itself, it contains any kind of infrastructure around the debug tools and everything running on an own simulator. So all of the modules included in our virtual platform is based on this SVP module. And this SVP module contains support for adding registers, including defining attributes and any other utilities that is good to have in a virtual platform. For example, it supports defining of attributes that we use extensively in the virtual platform for configuration, setting log levels and kind of stuff. We can also access any attribute from software debugger, so it provides visibility to the software side. We also have our own version of a register model that is called ER register, ER for Ericsson. It provides all the regular accesses that you might need for a register. Actually, ER register is also an SVP module. Either you define it with or without fields, you automatically insert attributes for the register and its fields. And then this way you build up the attribute tree for the whole virtual platform down to this low level of a register field.
My name is Shushan. I'm a modeling engineer and also verification engineer in Ericsson. Now I'm gonna talk about performance evaluation we've done in Ericsson. Today we use the TIM, both LT and AT model in this performance evaluation. As Peter told you, LT is the loosely time model and there's less timing information inside. And the AT is approximately time model, so we add actual model timing inside AT model. We don't have a full roadmap for the AT model for the complete ASIC and boards because we see a huge amount of development time that we need to develop the whole chipset and the board. So we only select part of the system which is timing critical in the performance-wise, like the memory subsystem and bus system. We want accurate timing in those subsystems so we can know the bandwidth and the throughput of this part, which is the most interesting part for the early stage architecture exploration. For the LT, we used it to acquire soft load model. Then we can use it to dimension the system. Like you can, by acquiring the software load model, you can excise the TM's virtual platform, for example, and you can see the utilization of the, for example, the hardware accelerator cores, and you see with different setup of the number of cores, how many performance you can get. So it's a relative comparison, and so you can get a better understanding of your architecture. Performance evaluation, here's the definition from our point of view, and it's to quantify the service given by the system as a function of scenarios. And the quantifying service is the metric in this case, and scenarios is the stimuli that we get from software, real software. And performance dimension, so depends on the evaluation purpose. You can either do exploration or performance dimension. Exploration, it's kind of relative comparison, like we use the LT model that we don't need that much timing information. But for the dimension, you need much accurate models. In this case, we use AT model, so you can get the exact numbers, like how much bandwidth you get. This is the example of how we do the performance exploration. That's the relative exploration in the system. It's a whole chipset. Here's a very simple SoC. You have the memory here. It's the on-chip memory. You can also have external memory, and they have on-chip bus, and they have the on-chip processors. And of course, here's the real software that we get from software department, and we can analyze them, and we can generate certain patterns that's mimicking the real software. So we can excising the whole system, and then we see how the system is utilized, like the usage of bus, how the memory is used, and hardware accelerator cores. And can also be used in static analysis. This is the example of the performance dimensioning we've done in Ericsson. It's nominalized, so this chart on the x-axis, you can see it as traffic load. On the y-axis, it's kind of performance. You can see it as throughput. So the picture above is the performance simulation we've done using AT model, this TIM model, against the original RTR version. So you can see they are quite accurate. So that's why I say 80% accuracy, more than 80% actually. Then we did a lot of TIM model profiling. So we see actually there's a bottleneck in the resource handler, you can call it. So when you do a SoC, there are lots of distributed components. So sometimes you cannot schedule them in the best way. But fortunately, we found it in a very early stage. So then we did performance boost, RTR refactoring. Then we did another performance test. Then we compared the original RTL performance graph against the performance boosted RTL. Then you see there's like 30% performance boosting in the low traffic area. That's really fantastic. We found it in a very early stage. So now let's go into functional verification. Now we mainly use ART models for the verification, both in the hardware IP level, SOC IP level, and also in the SoC chip level verification. We have two phases. The development phase is when we build the top level test benches. So because the TRM model is available quite early, so we can use it to write test case softwares so they can excise each other. The software can get an idea of the hardware, and because the software, we sometimes even found bugs in the TRM model, so we can fix them in the early stage and increase the quality. And for the regression phase, when the RTL is mature enough and integrated, we can use the same software test case that's developed a long time ago and run it on the RTL simulation and also the hardware emulator, or even when we have the real chips, we can run the same software test cases. Here's a table give you how fast it's the runtime and the load time of the simulation speed. You see TRM ART model is like 80 times faster than hardware emulation and tens of thousands times faster than the RTL simulation. And because it's fast, so when you develop in the test case, develop and the runtime loop is really fast, so they can produce software very efficiently. Let's look into the little bit details of the chip level verification framework. So we use this software-driven verification because the TRM, we can have software early, and the same top-level verification framework can be used for both or TRM, RTL, emulation, and the real hardwares. So actually, from the software point of view, they don't see the difference. You can just set different flags, so they are actually running on different targets. By having this, you can have the freedom to run software on different platforms. So it's increased the productivity, I would say. You can choose maybe something, when you do the first version debug, you want to just run the test fast. You can use the TRM. Then when the designer think everything is fixed, you can just launch a new regression using the hardware emulator, or before, if it's before the real hardware is ready. Yeah, so the integration work is really getting more smooth. Now let's go to the hardware IP verification. So still we use TRM, we use the top-down approach. So in the first stage, we have TRM model ready. So we use TRM as a both reference and design the test. We use it to develop the test bench. And that's the high abstraction level, so we cannot stress the test in this case, but we can finish all the verification components in this stage. And when later the RTL code is ready, we can integrate the RTL immediately and run some basic tests to find some early bugs. And then we start to stress the test, and we will find more bugs, and that's the verification loops. We have a lot of problems in the scoreboard where you do the checkings between TRM and the RTL, because one is implementing transaction level, another is the signal level. So for some of the problems, we can fix them very easily, like this out of order transaction, because the TRM is lack of timing. So sometimes they are out of order, but the scoreboard can stack them and they can be checked in the later time. So we don't use a very strict scoreboard, but we think these mismatches are allowed. There's one special case, we call it state divergence mismatch. That's because the internal state of the RTL and the TRM, they diverge. And those mismatches are very hard to say which one is correct or which one is wrong, because sometimes they are both correct, but just because they are in different state. Here's a picture show you the abstraction level and development time of the LT and AT model. So for the AT, it has a very low abstraction level but high development time. For LT, high abstraction level, low development time. So here's some question we need to answer is if we need to go to the AT for the verification, we say no. And to maximize the model reusability, because we use the same model for software and also for verification. For the AT, actually, we spent a lot of time actually just model timing. Actually, the functional part, they are almost the same as developing the LT model. Actually, AT has a quite low reusability in this case. Here's an example how we solve the mismatches between RTL and TRM. So for example, you have a function or have a block, input, output, internal. When you model AT, you just model functions with very few timing. But sometimes you have functions like G is time dependent, like arbitration and slotting time duplexed. So in this case, the LT model is not accurate enough, especially when the block is like a cache. Once you have a mismatch, they just state divergence, they just goes to complete different states, and you will never get match again. And what we do is we add another interface, we probe signal from RTL to drive the TIM. So here we have a latch. We split the function G into two atomic time-independent functions. So we listen on the signals from RTL. The RTL actually do the real decision and drive the TRM in this case. And by doing that, we solve a lot of problems actually. We can increase the coverage. And by also doing that, we don't need to model the AT, but we also decrease the abstraction level of the model. So we can meet the verification goal from doing that. And we also add checkers in the TRM. So once RTL do some decision, TRM will check if it's legal or not. If it's not legal, it will give an error. And people can look into exactly which point the error occurs, and they will trace back and try to debug. And that increases the observability for debugging. And of course, by doing that, you create some verification holes in the system. For example, the place you probe the signal, actually you just trust the RTL, but you should not do that in verification. So we will decide for that block, we will use other approach like formal verification to verify that block to make sure all the parts are covered. And another thing we see is these interfaces now are quite customized. But if we have later we have some CCI, for example, maybe we can improve the way of doing this to get it more standard. Here's the summary of the use of TRM in Ericsson. We think LT adds value to both software and hardware, and we have hundreds of users now already. And for verification, we only use LT, and LT also used for performance evaluation. But for AT, we only using certain level of performance dimension for certain blocks because it's very expensive.
I'm a system-level modeling and verification expert with Cadence Design Systems in Munich, where we essentially develop customized technologies, system-level technologies, methodologies for customers. So if you have a problem with your design flow system-level wise, you can actually hire us. So I'm here to talk about the state of art in virtual prototyping. Before I joined Cadence Design Systems like 6 years ago, I used to be a system architect for image and multimedia architectures as well as network processing architectures. When we look at different application domains and the kind of systems we have today, we find systems like this. This is a wireless handheld device with board, which has quite a collection of different embedded processors. There is a multimedia processor on the board. There is a modem that does a file-level communication protocol stacks. There's a bunch of smaller programmable accelerators. And then there is an application processor that has up to 4 different processing cores to run user applications. And the protocol stacks in these systems are quite diverse depending on the use case, on the application, right? We have the user application code, which may run like a standard operating system, or we have the communication protocol stacks, which have a real-time operating systems. And yet, then there are all these smaller cores here that have some sort of somewhat more enclosed firmware software stack running on them. The next example would be Infineon's Audo and Aurix SoCs that are used in automotive. The first generation of them had a single processing element combined with a whole host of different I/O and peripherals to fulfill its functions. The current next generation here already has 3 of those processing elements that run concurrently. Infineon itself states that their focus is on creating an efficient multi-core system which is best suited for hard real-time automotive applications. So in this case, it's not about a pure number of cores, it's about reaching real-time requirements. And the last example is, coincidentally, a wireless base station, an exemplary system which may have for multiple communication standards and scale with the different protocols and also the different cell sizes. The next generation of the system, compared to the last one, is required to consume much less space, and also even more power savings are required. This should be achieved by using a single hard and software platform, which scales from SoC board to the board level in different system configurations. And of course, here too, we find lots of software in the control as well in the data path of the application. So when asked how a virtual prototype has to model today, then this is like the system that comes out tomorrow, right? And what we see here, that most of these systems actually are based on scalable hard and software platforms. They have an increasingly programmable functions on board. This can go deeper into the data path of such a system or even into individual I/O functions. Software for these systems is distributed across the many cores in there, and actually more than 2/3 of such a system in terms of its development effort can be located in the software development part. Okay? We continue to see the usual issues, which are like low power application performance optimization kind of questions, but it's even more the productivity, right? If the complexity raises so much, how do I continue to design such systems with the same workforce, essentially, right? And of course, there is this whole verification bring up kind of issue, like how do you verify that the hardware and the software work together? Let's look a little closer into the automotive domain. In automotive, we have a growing vehicle, electronics content in the vehicle. This is facilitated by trends, by so-called mega trends, such as the intra-vehicle networking, the consumerization, that is the car talks to you, with you, and then there is the car connected to the Internet of Things, the car talking to other cars or to some stations. With this, already today, we have the software content in the car to be the biggest single contributor to the overall product complexity. What it means can be shown on an example like this one. This actually is the latest VW high-end sat-nav system called RNS 510 that came out just a while ago, and it was reported to have blackouts and long interface switching latencies by users. And this was caused by performance issues in the main processing core. The problem is not that there is a performance issue. This happens all the time during the development. The problem here is that this was discovered so late, which caused quite some loss in image and revenue. Parts of the explanation for such a late problem could be the supply chain in automotive, which is this kind of vertical supply chain, which is distributed across multiple vendors. All the system knowledge can actually be found rather on the top of the supply chain, while the software content increasingly is generated at the bottom of this chain. And this observation actually is confirmed by the suppliers itself, who propose to use a virtual prototype as somewhat as the common language that helps them to align across this supply chain. We at Cadence have created a virtual prototype at the ECU level. That's the electronic control unit. Essentially, that's a control unit that does a particular function in the car. We have used a hardware platform, which is the Xilinx Sync 7000 platform, comprising 2 ARM processor cores as hard macros, together with some PGA fabric for your user-specific code. We can use this platform to run automotive applications such as the traffic sign recognition, which essentially performs a set of algorithmic steps on an image stream to detect like a traffic sign and bring it into your dashboard. So then such a function actually can be mapped onto software running on the embedded cores or onto hardware running in the customized logic around it. This virtual prototype modeled in SystemC can then be compiled and executed on a plain notebook who runs Cadence simulation engine. When we look at the modeling complexity of such a platform, we find this to be quite moderate. There are about 45 different TLM models in this platform, which are instantiated about 80 times. And the TLM models together have about 250,000 lines of code. This sounds like a lot, but in fact it's not, because most of this code actually was automatically generated to describe this 7,500 software visible registers in all these peripherals. So using this platform and running applications as the one I have just shown, we can actually boot quite a host of different operating systems, unmodified, and we actually run faster for many of the software workloads than the real hardware. So if we can do all this, what is the problem with virtual prototyping today? I have chosen another example from network processing. In network processing, we find systems like this one, which essentially has a bunch of so-called line cards that have communication protocol interfaces. Then there are data path processors that deal with the handling of packets. They are controlled by a control processor, and all these line cards are connected by a backplane system. Such a compound of systems can be described best as heterogeneous multiprocessor or many-core architecture. We find a host of embedded standard cores, such as ARM, MIPS, PowerPC in there, but we also find a collection of proprietary cores for DSP functions or microengines for packet movements. Potentially, there are hundreds of processing elements in an SoC or on multiple SoCs per board or multiple boards in such a system. The software for such a device actually is modularly structured as you would expect it. So there may be multiple operating systems running on different processors. The software follows the usual abstraction level. There is like the operating system, hardware, abstraction layer, hardware-dependent software, firmware, you name it. And of course, there is a heterogeneous development environment which in parts may be proprietary to debug and bring up this whole thing. Designing the next generation platform actually poses 2 unique challenges. On the hardware side, we face the fact that the size and the complexity from generation to generation of these systems constantly increases, which stretches us thin on the traditional RT development and verification flow, because we just need some more resources, licenses, simulation hosts, and so on. On the platform software side, the problem remains as it always was. Such a complex hardware is notoriously difficult to understand for software developers, and it's really hard to write software for such a platform, which leads to long lead times due to the low-level hardware-software integration issues and also to quite late software availability, which means it has an impact on quality, performance, and the time to market. To address these issues, one can actually switch to a SystemC TLM-driven development flow. Here we focus only on the loosely timed modeling step for the virtual platform. With such a flow, or the value proposition of such a flow, is that this traditional first the hardware and then the software development and bring up planning actually can be changed into truly concurrent plans where the hardware development and software development happen concurrently. Of course, this is only possible because we now have a critical path that runs from a hardware specification through the creation of a model back into the software. The trick here is that the first software can be brought up and tested on the virtual platform months before the real hardware actually is available. And then the hope actually is that you need only so much more time to confirm what you did on your virtual prototype with the real hardware. Having such a critical path through the models actually poses also quite some requirements on the modeling team. If you have such a huge platform with different SoCs and variants of SoCs, you are actually required to hammer out one model after the other one, following a continuous release plan. And that means you need to be really productive to deal with this kind of requirements systems. And our conclusion here was that one needed a modeling and prototyping framework that helps the creation and continuous integration as much as possible. The use cases and requirements for such a framework can be generalized to one very prominent case. And this is, you want to run such a system, which is complex for itself, connected to some sort of environment, also in SystemC, which may be a peer system, somewhat smaller, and connected to traffic generators and things for stimulus. Such system should be distributed onto a collection of different SystemC simulators. And while it is executed, you, of course, to develop your software, want to connect whatever debugger you feel appropriate using for the particular task at hand. It could be RealView to talk to an ARM core. It could be GDB if you want something more generic. It could be some proprietary solution, or it could be like the Cadence virtual prototyping GUI that allows you a unified debug of hardware and software together. In addition to this use case, of course, there are the usual suspects, meaning in such a framework you want to develop and verify modules, you want to create platforms, but you also need a path into the implementation. So it's not just the software development, but software development definitely is the most important use case here. To address these requirements, we have developed a virtual prototyping framework, which actually was meant to be open, modular, and scalable. It's open because we aim to use its only established standards wherever possible. This is SystemC, TLM, IPXACT. And then deploy common libraries and programming patterns as much as we can. We wanted it modular so that we structured it in independent components that can be used, mixed and matched depending on the use case we plan to use it in. So the idea here was that this framework actually should not constrain you on your particular TLM flow. So we structured it into independent components called facets that serve a single purpose each and provide clean interfaces. The facets for the framework we found necessary, in addition to the SystemC TLM capabilities that we have today, are essentially extended logging reporting, attribute handling and configuration facilities, a factory for the dynamic model creation. Then there is some encapsulation of model and simulation lifecycle management. We have provisions for a decoupled control and execution. We'll explain this in a minute. And we have an extended debug interface. Last but not least, capabilities for a distributed simulation. I don't want to talk too much about modules itself, only so far. If you have a standard compliant SystemC module, you can use it in this framework. If you want to use the extended features, it's better that you follow a certain modeling guidelines. There are like about 11 items for the framework. And you should better derive from a common parent to bring in additional facilities. The idea here is that this framework essentially forms an overlay on top of the SystemC library. When it comes to dynamic creation and configuration capabilities, we are able to create a SystemC object hierarchy from a textual design description at runtime. This avoids recompilation and enables quick design changes, which is favorable if you have thousands of small regression tests that only deploy parts of your platform every time. So you can actually tailor platform variants without and consume fewer resources and run much faster. The right-hand side on the slide shows an exemplary description. So it would contain hierarchy, there's a type, an instance name, a set of configuration parameters, and of course you have to describe the binding of modules to each other. Execution modes for the framework are standalone batch mode, which you use for regression testing or module development. Then there is the common known integrated execution mode, meaning you have a simulator that is tightly integrated with the simulation model itself, such as Cadence SimVision, and you can actually access all model and simulation state at any time for debugging purposes. We call this the GUI mode here. And then we have a remote decoupled way of executing this, which essentially means you separate control, configuration, debug, and all these processes more clearly from the simulation process, potentially to enable remote access in geographically distributed settings. Remote control is interesting insofar that the framework provides a server which gives access to the simulation by exporting a modular structured protocol interface for the facilities. So if you open up the creation and simulation aspect, then you can access this one remotely. An attached client provides a generic interface to this framework function, meaning we have provided an API, a client here, that can be used by arbitrary user or debug tools. Server and client communicate over inter-process communication channels such as TCP/IP sockets using object serialization. One example, important example for this kind of solution is shown here. That's the common debug interface. In the back end, our framework debug interface actually provides support for heterogeneous core. So it provides a core type independent interface. This has a representation on the model level, which can be used to remotely access this cores from a native debugger in the front end. Or we can access them also from an integrated debugger, such as through the Cadence GUI, through some other channels. So the remote solution here actually provides something called a debug handler, which serves as a debugger proxy within the simulation process, and a client handler here, which technically serves as representation of the model towards the debugger. Our framework provides support for distributed simulations. This is achieved by manually partitioning a design and loading the parts into different simulator instances. We have a concurrent model interface called COMIX, which provides a link between the simulator instances. The function of this link essentially is to map TLM SystemC connections into this communication channel and also to manage the life cycle and synchronize the simulators. COMIX, the concurrent model interface, actually has to deal with both sides of a communication TLM or SystemC communication link. The left hand of this frame slide actually shows how this is done for the NB transport protocol. Here's the cut, and depending on the state transitions, the COMIX needs to satisfy the TLM protocol. Using COMIX, we can achieve reasonable speedups that, of course, depend on the computational load distribution in the system. Meaning, if you have a communication-dominated system, then distributing your application, your model, may actually slow you down. These are not the only features that one needs to support this generalized embedded software debug use case. In addition to this common debug interface and the concurrent model interface, we would also need things like an segregated configuration and control, meaning we would want to be able to attach multiple debuggers as peer. And we would need something like a director, which essentially enables a single debug interface into a distributed simulation. Putting these things together, one can create virtual platforms such as this one. There are two SoC examples that have a couple of processors. and run some demo application protocol stacks on them. One can assemble the system, bring it up, and actually attach debuggers to it. You can use for each core, you can use whatever debugger you find meaningful there, or you can use, again, the unified debug interface to look at the cores and the hardware altogether. This framework is in production mode today and has been used to actually create quite a collection of different platforms. We have smaller ones comparable to the demo system we have just seen, or even our Sync automotive platform with 44 object instances. This is the elaboration report of these platforms. But they range all the way up to about 5,000 SystemC objects in a single simulation. So here's another reason why you actually want to think about distributing a simulation onto multiple instances, just to keep the resource requirements manageable. When we come to look at the modeling effort in terms of the lines of code, we see that the systems range quite widely in their effort, from 16K to 80K. This is not including any of the processor code. It's just the TLM models. We also see that there is some reuse between the different systems here. For some reason, this doesn't seem to be generic, but more or less application specific. Focusing more on the framework side over here, we find that we could implement all our additional facets with about 8,500 lines of code, and there are another 2,000 lines of code which we spent on implementing the remote tool client. The breakdown for this one looks like this. Concurrent model interface features about 20% of this 8,500, which should amount to 1,700 lines of code. Attribute and factory handling system is about another 20%, and the remote access facilities are about 30%. When we compare this with SystemC 2.30, we see that SystemC 2.0 has about 80,000 lines of code, including TLM, and we are at about 10,000 lines of code. So our overlay technology seen in this context would amount for 10 to 12% of the combined solution. So to summarize this in terms of the things we know about virtual prototyping and the things we still don't know. We have seen when we model IP that we know how to create TLM models. There's the SystemC TLM standard, and we know how to even generate IP modules from higher level descriptions. However, there are no common modeling guidelines for TLM models. So you never know what you get when you buy one. There may also be extensions needed for the standard. But for creating a model, you still depend on the right mix of skills for your developers. If you get a software developer to do it, it's usually running fast, but the concurrency is a problem. It's done by a hardware developer, then all the details, maybe more than you wanted. Okay. Usually we understand well what the different abstraction levels mean today. We know how to stepwise refine them. There are mixed level flows. There is a connection to acceleration emulation, and there is a path into implementation. However, similar to the example we have just seen, one often needs different models for the different abstraction levels. There would be a better way for timing estimation and annotation needed, because this is what this transition here is about, performance estimation. So if one can find a solution here that does not require remodeling, it would be good. When we look at the platform assembly, usually we know how to compile a static SystemC netlist that may be manually written or generated, transformed from some sort of textual description, which could be generated by tools. Dynamic model creation at simulation start, so as I just shown it, is already something, but of course it would be much nicer if we could modify or create models dynamically at runtime. And of course, this shouldn't be an ad hoc solution or overlay technology. It would be better to have this as a tool feature or even part of the standard. When it comes to configuration, there is the Accelera CCI standard, which seems to be doing a good job when it comes to model parameters, mem size, verbosity, these kind of things. The only thing we have been missing here was maybe a more intuitive support for the basic data types, the functions of the basic data type. Example is the string handling, so you actually want all the string operators usable. When it comes to simulation control and introspection, the thing we know how to do today is how to run a SystemC simulation in an integrated single simulator cockpit, which allows access to all hardware and software state. And this could be the command line with GDB. That's no difference. The problem here is that multiple tools usually run mutually exclusive, meaning whenever you are interacting with one of the tools, the other one may be frozen. That's the case when you have a processor in the TLM model breaking on a breakpoint and handing it over to the debugger, then there's nothing you can do in the model. It's frozen. This is no good. Multiple tools should be able to run concurrently, access the simulation state without, messing each other or the simulation up. Debug interfaces. Each debugger and core pair usually has its own interface. This holds for a family of course as well. What is needed is a vendor and core type independent debug interface. 4 settings as I just have shown it. And of course then there's the last point here, distributed simulation. SystemC unfortunately is a single OS thread, and that's the root of all problems. We need some way to either distribute a model across multiple simulators, as I have just shown, or distribute a simulator across multiple hosts. And this concludes this talk. We have seen virtual prototypes ease the system integration if you use them correctly, even along a vertical vendor chain as in automotive. In general, the value proposition is better software and faster time to market. I have also shown examples where they can run faster than the real thing. Creating virtual prototypes still is a work of art, meaning it depends on the expertise of a few experts. The deal here is you have to be careful about how you trade off hardware visibility versus simulation speed. That's the core of it. And in order to deploy a TLM methodology successfully, you depend on a productive creation of complex virtual prototypes. But that's only the first part of the story, the development. But then you have to support the deployment of these virtual prototypes, meaning you need to support heterogeneous debug scenarios within your simulation environment.
Okay, first apologies for my voice because I catch the cold in the plane. Hopefully you can follow a bit. So, a bit of a strange beast perhaps in this highly digital-centric session. I will give you an insight in SystemC AMS, analog mixed signal extensions available for SystemC. As you know, we can model hardware, software, processor-oriented systems, but there is much more to it if you are modeling your entire system. Can be even the application. And in some cases you would like to include the analog part, or at least an abstract view of your analog subsystems or radio subsystems. So don't be scared, this is not about SPICE or low-level transistor stuff. This is an abstract modeling style which you can incorporate in your virtual prototypes. Quick overview. We dive a bit into the language standards. I will give an introduction on the different models of computation which are available, and then you will see clearly this is about abstraction of analog mixed signal behavior. We have last year updated the standards. We have now AMS 2.0, which offers much more dynamic features. And I also will give an example that you see some code on, in this case, a DC motor control system using a PWM circuit. So what are the objectives of SystemC AMS? I think you heard some nice stories before on virtual prototyping and how you can model analog or hardware software systems. At the end, SystemC AMS is an extension of those platforms and bringing in the AMS piece. So it is targeting system level modeling, methodology which is compatible with ESL design styles as we see it in the industry. It is about architectural modeling as an architectural design language. And because SystemC is C++, it also is then very easy to facilitate a model exchange and IP reuse. So that means especially in automotive, shipping of SystemC AMS models to the customer is becoming very straightforward. And last but not least, the abstraction styles introduced with SystemC AMS result in a very efficient simulation approach. So we always aim at no serious simulation penalty if you include AMS. So what are typical application domains for SystemC AMS? Communication systems, especially wireless systems, can be near-field communication, can be GSM, LTE, wireless LAN, that kind of systems. All those systems have a radio interface, which is very often digitally controlled. And you want to model not only the analog standalone, but really in its environment where it is controlled by the baseband or by the software. Imaging systems, so sensors, displays, LCDs, especially the image part is highly analog. For instance, ST is doing a lot with SystemC AMS for modeling those type of applications. And I already mentioned automotive, especially for the modeling of electronic control units. So for power management, but also for in-vehicle networking, you see more and more the use of abstract languages centered around SystemC. Some history on SystemC and SystemC AMS. I think the left side is well known to you. SystemC is already there for more than a decade. And in the early days, we are talking about 98 to 99. If you look at the AMS extensions in the right side, it has a similar type of track record. Not many people are aware of that. Many people think it's a new language. It is still in its early phase. I would say not at all. Because of the, let's say, 10 years of development in that area, it has been proven, it is robust. And what you see just at the bottom is we are moving to bring this standard to the IEEE. So it has now been, within the Accelera organization, we have released 1.0 and 2.0. So now time is right to bring the standard into the IEEE. So we have started a working group called 1666.1, so that this is becoming a .1 standard of the existing SystemC language. So in terms of positioning, a bit of the conclusion. So we clearly position ourselves at what we call at the architectural level, where you want to model your system at an abstract way. So you could already do that for digital systems. And now with the AMS extensions, we can incorporate abstract analog features inside such a system. A small diagram on how such a system looks like and what are the properties. So here you see a communication system which has, let's say, an antenna interface, radio functionality, and the more, let's say, in the back end you see all the digital functions. But there is more and more control in those type of radios, calibration and control. You see microcontrollers for testing. So how do you make that happen if you want to model that? So you could give it a try at the implementation level, but you will soon find out that existing HDL languages are not suitable there. So what you want to model is, at the end, the interaction between your hardware-software stack and your AMS subsystem, especially the signal path. So does the signal really go through the system? Also looking at performance type of effects. And there is, of course, for SystemC, you have a lot of control and digital communication. So at the end, what we bring together is plain vanilla SystemC, transaction level modeling, especially for the communication at the digital side, and the modeling of the radio front end using the AMS extensions. So what we see what are the drivers of all this? At the end, modeling of what we call true heterogeneous systems on chip. So I already explained that, analog, RF functions. But what we also notice in the industry is that the frequencies go up, the bandwidth goes up, especially with radio interfaces. Configuration of ICs, with more and more digital on board, you can also control the analog and RF functions much better. So all that requires that we really revisit the way we model and design those type of systems at the system level. For that, it's crucial that we have proper design abstraction levels, so I will dive into that later. And I always get questions, okay, what are your use cases? Are they different or similar? Then I always say the use cases are similar as in the digital domain. So yes, you want to make an executable spec of your system, but now that system includes analog RF components. You want to do your architectural exploration, you want to dimension your system, you want to look at performance criteria, you want to do virtual prototyping and already give an estimate on what it means for the verification of your integration. So at the end, we are aiming at bringing SystemC AMS inside the design approach of virtual prototype creation. And of course, key is there that we have abstract views. I think what are the advantages? I think that is obvious, right? You all know SystemC, so having a C++ under the hood brings you a lot of power in terms of libraries, the way you can do object-oriented programming or modeling. What we introduced for AMS are some basic building blocks, what we call analog primitives. And as this runs, you can run this in a commercial environment, but you can also, using the OSCE simulator, there is also a proof of concept simulator available in the open market. So this can also, let's say, tool independent. Modeling, especially mixed signal, analog, digital, very often there are commercial solutions following co-simulation, which are in some cases quite cumbersome. Also the API is not always very straightforward. So having everything based on one foundation, which is SystemC, really makes sense. And as this is, of course, open and it can be extended and is standardized, I would say it's a very transparent and very clear modeling platform for the user base. Different use cases on top, if you have touched on those, the executable spec, architecture exploration, especially in the mixed signal domain, we basically identify two main categories: sampled system, discrete time, or continuous time. So analog systems are very often continuous time. Then in the analog domain, you have energy preserving effects. That is what is called conservative behavior, but that is not always what you want necessarily need. So that can be also described in a non-conservative way. So if you do the split right, you end up with a minimal set of 3 models of computation. So we defined a data flow engine, which makes simulation very efficient. We have a linear signal flow, which covers the continuous time non-conservative domain, this region. And then we have the third region, continuous time conservative behavior. And then you are in the what you can call the traditional electrical linear network domain. And there you are solving your Kirchhoff laws. But this is, of course, the area which you would like to avoid. You would like to be as abstract as possible. So therefore you model very often in a discrete time manner using a non-conservative modeling style. What does that bring in terms of simulation speed? Here a bit of a study we did based on some material we got also from industry is, yes, you can do everything with SPICE, but simulation takes really weeks if you're lucky, or months. Yes, there are languages like Verilog A and Verilog AMS, so you can speed up, and that is a factor of 100 to 1000, but it is still not really sufficient if you want to virtual prototyping, where you want to be close to real-time simulation. So there you should talk about factors of 100,000 or even a million times now, and that is the region where we are talking about. And of course, it's a bit of difficult to compare apples with pears in this case, but if the abstraction is right, so we use a data flow model of computation, we can really target high simulation speed, and that inclusion in virtual prototypes is really possible. SystemC AMS is supported. There is a language reference manual, which is similar to the SystemC reference manual, defining the different components. We followed a similar type of structure, so we also have modules, we also have interfaces, we have some analysis types. So you can download this from the Accelera website. And for the users, because this is still for many people new, we have also developed a user guide, which is basically a sort of training material, which gives a much more background on why certain modeling styles are used. And we touch on the different models of computation and also how you can do AC frequency domain modeling. It includes examples and even some small systems. And what we see in practice is that this type of guides really are beneficial for new people, because on the Accelera forum, for instance, we get many questions and we can say, oh, you should just read chapter 5 or chapter 3, and that is very convenient. Here an overview on SystemC and SystemC AMS. So we are based on the plain SystemC language, and of course you can make your virtual prototypes or mixed signal virtual prototypes using all the SystemC goodies. What we basically add is this piece. So we have time and frequency domain solver. We have dedicated schedulers or solvers available to support the 3 models of computation I already mentioned. So the time data flow, the signal flow, and the electrical linear networks. So with that we have a comprehensive solution to bring in AMS at the system level. In view to time, I skip or quickly go over it. I already mentioned that we have, let's say, components and objects similar as in the SystemC world. So you will recognize the modules, the ports, but we have the prefix SCA for the AMS extensions. And you also see that we use the namespace to identify the models of computation. So we have SCA TDF for the time data flow model of computation, but ELN for the electrical linear networks. So we have nodes and terminals. But in that sense, coding SystemC AMS functions is quite similar to coding of SystemC modules. What we have done in SystemC AMS 2.0 is that we have identified, based on customer requirements, that it was a bit too static. Data flow, for those who know it, it's a modeling style or a model of computation where the schedule is computed prior to simulation, so you have a static schedule. And that is very efficient, but it also has some drawbacks, especially when you have to interact with dynamics in your system. So what we have done, we have extended the TDF modeling style by some new elements to make it much more dynamic and reactive. So changing time steps, signals which sporadically change, we can now cover much better. So for instance, here an example of a motor control system. So where we basically have a system with a loop, where there is a control block, pulse width modulator, and the description of your DC motor. At the end, this type of control loops where you have to define very accurately how your pulse modulation, what the duty cycle is. If you want to control it in a good manner, I think we need those type of extensions. So here you see the end result of the signal that comes out of your pulse width modulator. You see that indeed the pulse width changes, and you see the current through the motor, which is going to settle and reaches its final state. So this type of systems you can now easily model with SystemC AMS. Some code snippets for those who are interested in to see how does it look. So you see that we have normal SystemC modules have a SE module. We have a dedicated TDF module, a macro SCA TDF module, where you instantiate your port, your constructor, and we have dedicated callbacks to set the attributes and also to change the attributes. What I indicate here in red are the ones which are introduced in AMS 2.0. And similar as in SystemC, where you have the next trigger function, we have a similar type of function, what we call request next activation, that we can really activate the analog computation at the moment we want. And that means that we only compute at the edges where the signal changes. And the advantage of this type of things is that normally we have this very fine grid to be able to see the pulses, but that of course gave a lot of overhead. If you then have to basically oversample your signal, your time step is way too small. So you see per cycle we needed 500 activations, whereas for this dynamic TDF mode we only need 4. So in that sense, just by introducing this feature, we can already make the models even more efficient. Quick glimpse on SystemC AMS. So where are we with that? I think SystemC AMS is well supported and driven by European industry. So you see that NXP, ST, Infineon and Continental are the main drivers there. The domains I mentioned, primarily in the communication, automotive and imaging system design domains. It is a mature and proven standard. It is already out there for 10 years or so. AMS 1.0 was released in 2010 and 2.0 last year, introducing all those dynamic features. It is ready to use. There is an open source proof of concept offered thanks to the guys in Fraunhofer in Dresden in Germany. So if you want to play with this, it is available under Apache 2.0 license. And I think what is also very nice is you now see also in the industry that the first commercial solutions are appearing. So for instance, Fraunhofer offers an environment, but there are other commercial EDA vendors also offering SystemC AMS support. If you want to know more, accelera.org, but you can also look at the downloads areas for the standard, and there is a dedicated systemcams.org website which is driven by the community.
My name is Donald Cramb. I'm with Synopsys, where I'm primarily responsible for supporting the ZeBu emulation product line. What I'd like to talk about is a little bit more detail about how we actually integrate virtual platforms or virtual prototypes with what we call transaction-based acceleration. So first couple of short sections, I'll try and give you an idea of what we mean by transaction-based acceleration and also virtual prototypes. I know most of the people in this room are already very familiar, but just in case you're not, plus it also gives you an idea where we're coming from in terms of virtual prototypes. Then short section why it's a good idea to integrate the two. And then the next section a little bit about how we do it or our customers have done it. What is hardware acceleration? Obviously, there's hardware involved. And especially when you talk about emulation or emulators, there really has to be an automated flow from RTL to the download image that gets downloaded into the box. Also, you should expect simulator-like debug capabilities. Even though it's hardware, you should be able to get similar waveforms, similar capabilities to your simulator. And then probably most key is it should run many orders of magnitude faster than simulation. Some of the common use models for hardware-assisted verification or acceleration originally insert emulation, where you physically had a system that the emulator will connect to, your DUTs in the emulator. But because of the speed differences between the two, typically you'd have to create some type of rate adapter. Then the next use case is embedded test bench, where pretty much the whole test bench and the DUT are running inside the emulator. So there's no interaction between the emulator and the outside world, apart from maybe some very simple low-level test bench. Then co-simulation is where you have test bench running in a simulator on a host workstation, the DUTs in the emulator, and the interface is pretty much cycle-based. So every cycle there's interactions between the DUT and the test bench running in a simulator. Simulator could be an HDL simulator or, of course, SystemC. And then what we're talking about here today is transaction-based acceleration, where the interconnection between the test bench or the virtual prototype in this case is over more of a transactional interface. And there is a standard, accelerator standard called SCIMI, which supports actually two levels of communication. One is a macro-based approach, SCIMI 1, or a DPI-based approach, SCIMI 2. So what are the key elements for us for transaction-based acceleration? One is high-performance test bench, because, of course, the emulator is going to be running, hopefully, very fast, standalone. And then also optimizing the communication between the test bench and the DUT. This can actually have a very large impact on the overall performance. So we look at the impact of the test bench. If you've profiled your environment and your test bench is taking up 50% of the runtime in simulation, and 50% is running in the DUT, even if you accelerate the DUT so that virtually no time is being spent in the DUT, the fact that the test bench is running at 50% of the overall runtime means the maximum, according to Amdahl's law, the maximum speed up you can get in that environment is 2x. So, of course, the raw speed of the test bench is key. So if you look at cycle-based interaction between the test bench and the DUT, what you see here is the test bench runs, there's some communication happens between the DUT and the test bench. The DUT does its thing in the emulator, and that happens every single cycle. So you can see there that there's a huge amount of overhead between the emulator and the DUT. Test bench acceleration, you only interact between the DUT and the test bench when required. So basically, you're trying to create as much parallelism in the environment as possible, so the DUT is running while the test bench is running it, and vice versa. And by the way, I'll get to the systemC part in a minute. So virtual prototypes. So to us, it's basically any software model, C, C++, or SystemC, I told you, of a complete system. Balances accuracy against execution performance, and we've seen that in an earlier presentation where LT, AT has different trade-offs between performance and accuracy. For us, the minimum accuracy required for a virtual platform, because most of our customers are focused on software integration, software development. The level of accuracy in the virtual platform needs to be at least enough to run real unmodified software images. For example, boot OS, run drivers, run applications. And what this typically means is that the virtual prototype needs to be at least register and instruction accurate. What we've seen is typically, and we work with a bunch of virtual platforms, both open source and proprietary, and not just ours proprietary. But typically we see these platforms run about 75% of the host system and employ a bunch of different modeling techniques and communication mechanisms. Another important part for our customers for the virtual prototype are the system interfaces. Because most of our customers are software developers, they want to see the impact that the environment has on the virtual prototype and vice versa. So they want to see things like real virtual displays. They want to connect up the DUT to a real network. They want to plug USB devices in and see that from the DUT. Typically what's not modeled, detailed timing, caches, for example. An open source example of the type of virtual platform we're talking about is the Android development emulator, which is based on QEMU, which is an open source virtual prototype. So just to give you an idea of what a virtual prototype looks to us, you have a CPU running as an instruction set, a simulator, a bunch of peripherals connected over some type of bus, and some virtual interfaces. Okay, so why do you want to integrate virtual prototype with hardware accelerated RTL? There are many reasons, but the two we see the most, and again, as we saw in an earlier presentation, there's huge values in virtual prototypes early on in the development flow in terms of having very fast models which allow you to do a bunch of stuff, but it gets to a point where you actually want more accuracy within your environment. And that's where adding the cycle level accuracy of the DUT within the emulator begins to provide value. Then from the other side, emulation is most effective within an environment where the tests are long or there's lots of interactivity between the user and the environment, which means that you're typically running at system level. But running at system level, getting all the capabilities you need, the test bench can be very complex. Just so happens there's already out there a bunch of these test benches already built, and that's virtual prototypes. And again, from an array of proprietary implementations to open source. So if you look at virtual prototype as a test bench, as we just talked about, they're fast. The interfaces between the virtual prototypes and the outside world tend to be protocol specific, and so most of them are transaction level or transaction based. And we talked about earlier, these things are capable of running real software stacks, running real OSs, and have a bunch of virtual devices, virtual interfaces. The other side we just talked about is you have your virtual prototype, you've developed a whole bunch of software, you're now ready for more accuracy in the system, and that's where the accelerated RTL comes in. The hard part is how do you integrate the two? Use a very simple example just to walk through how we handle this integration. So if we take a simple video decoder, we have the DUT, which is a controller, memory, ROM, the virtual prototype, which is running the CPU, running an OS, running the software. And then on the other side, we have a display component where we have implemented a virtual display. The basic glue that brings the hardware side, the RTL accelerated side, and the virtual prototype is something called a transactor. It's a core of transaction-based acceleration. And the transactor basically has two parts. One is a software side, which talks to, in this case, the virtual platform. And those APIs are in a range of languages, but mostly SystemC, C, or C++. And then on the hardware side, according to the SCIMI standard today, the bus function model is described in System Verilog and is modeled at a cycle level. And then underneath, the communication is implemented as a low-level, high-speed messaging system. So once you have the bus function model in System Verilog, it's then the vendor's job, if you like, to take in SCIMI 2 DPI functions and synthesize those to something that's implementable within their emulator. So you as a transactor developer are faced with a DPI interface. You don't have to worry about any of the underlying mechanisms. That's the vendor's job. So in terms of our simple example, we have a couple of transactors here, an AXI transactor, an HDMI transactor. Actually, I think most virtual platforms work in a very similar manner where from the software side, all peripherals are seen as basically objects or memory mapped objects. So that when the CPU wants to access a peripheral within a certain memory location or range of locations, callback functions get called, and then it's within those callback functions where you actually interact with the software side of the transactor. This callback function does a range of things, including, for example, PCI. It will do further address decoding. It's responsible for sending and receiving the transactions from the hardware side, but again, at a DPI type of level. And then there's other capabilities you can add, like transaction analysis, inject errors. And then the last thing is it can provide the interface to virtual devices. Like, for example, it can call a function on the virtual display object to display a frame that's just received from the hardware. So going back to the AXI transactor, in our implementation, but again, ours is just one implementation. It's a C++ library with a lot of public methods, but a lot of capabilities built in. So just a little bit code. This is probably the simplest example you can have in terms of using Synopsys transactor, but you can see there's a number of different capabilities. And you get down to the interesting part where you're actually sending data over the AXI bus and then reading data over the AXI bus. But the thing is, even with that very simple example, and if you consider the complexity in a typical SoC, managing those APIs, because they're typically protocol specific, can become cumbersome. So in terms of the hardware side integration, typically involves some type of top level wrapper which instantiates DUTs, transactors, things like clock ports. This is our implementation. I know some of the other vendors have different implementations on how you bring the two together from the hardware side. But like I said earlier, the BFMs are typically implemented in System Verilog. And most implementations support some level of behavioral code, like implicit state machines, unbound loops, that type of thing. And as I mentioned earlier, the standard today is SCIMI, both in terms of a macro-based approach and DPI-based approach. So just say a little bit about the communication infrastructure. The lowest level, typically you have a physical connection, which is vendor-specific. The transaction level, based on SCIMI2, which is the vendor's responsibility to implement. Then protocol, the BFM, actually does the transaction to cycle-based conversion. And then, of course, the virtual prototype. So as I mentioned, even though there are transactors out there, there's really no standardization in terms of the transactor API, even within Synopsys, unfortunately. So in terms of complexity of a real-world SoC, if you have a lot of interfaces, then the job of managing that can become pretty difficult pretty quickly, which is why using TLM is a good idea. Basically standardize those interfaces, make the whole job of managing it easier. Told you I'd get to the SystemC part. And then again, you probably know more about this than I do, but using TLM2 enables interoperability. It's targeted towards memory map component models. So not all of the interfaces we just talked about are compatible, but a lot of them are. Provides generic data structures and API, and supports, as we heard earlier, multiple timing modes, loosely timed and approximately timed, as well as cycle accurate. So this is an example of how our customers have actually integrated our transactors with SystemC TLM. And it's basically a layer on top of the existing transactor API, which maps that protocol-specific API to TLM, standard TLM, possibly with extensions, but TLM. So if you look at our simple example, like I said, basically it's just adding a TLM interface on top of the existing transactor. So rather than developing the transactor from the ground up, we have added this wrapper. And by the way, within a typical environment, it's also possible to support both TLM-based interfaces and just standard C, C++ API interfaces. As you see here, we have AXI where we've added TLM, and then HDMI where we haven't. One other advantage that TLM gives you, it's a whole range of tool support, both from Synopsys and other vendors. In our case, we have an environment where we actually created libraries of our TLM transactors, which you can use within a nice graphical environment in terms of platform creation, GUI focused. So it lets you place the components, also lets you set parameters and properties on the components in a very easy fashion. So once you've done the integration once, then it's very easy to reuse. And then within the runtime, again, you're using the capabilities of the tool. So in summary, transaction-based acceleration limits the impact of the test bench by promoting modeling at a high level of abstraction and optimizing communication between the test bench and the device under test. Virtual prototypes provide high-speed models for software development, software integration, and that's marketing stuff. And then using TLM2 simplifies the task of managing, creating, and sourcing platforms and components.
We're going to talk about using SystemC with UVM test benches. The idea being to sort of combine the powers of both languages into a single, what we're calling a hybrid test bench. In this case, hybrid simply meaning SystemC combined with System Verilog UVM. So we're going to talk a little bit about the case for hybrid test benches. We're going to talk about some of the standards that we leverage. We're going to talk about an open source package on our Verification Academy anyone can access called UVM Connect. It's a fully TLM compliant TLM2 and TLM1 way of interfacing the two language systems. We're going to talk about reasons you might have hybrid test benches, primarily reuse of legacy models, interchangeable test bench head, dual use drivers, and finally hybrid test bench examples, which not only the previous presentation, but some of the others talked quite a bit about. So we'll go over that as well. We'll start out with the case for hybrid test benches. What you've seen in this session today is that mounting use of TLM is a common interconnect for multi-language HVL test bench environments. The TLM2 standard is already baked into IEEE 1666 as well as System Verilog UVM. So they both have built-in support for TLM2 compliant ports through which you can send transactions. In addition, there are open source public donations for what I call a cross-language connectivity fabric, you can think of it, or a TLM fabric. There's UVM Connect from Mentor Graphics, which we're going to talk about today. It's a very simple package. It can be used with completely unmodified SystemC and UVM. You just compile it, link it. It's, open source. There's also a package called UVMML, which is being considered standard under the Accelera Multi-Language Working Group. I won't talk about that, but that's another example of a package that has some similar purpose. We think it makes sense to combine the strengths of the two verification methodologies, UVM and SystemC. Why would you use one or the other when you can use one and the other and combine their powers? So the power of System Verilog UVM is constrained random traffic, sequence generation, coverage, scoreboarding. Power of SystemC is it's a good interfacing language. It's C++, so you have access to all the resources of any Linux host system, networking, disk, X Windows, device drivers, etc. And it's also a very good glue language for virtual platforms, which the previous presentation talked quite a bit about. Reuse of legacy IP models. Oftentimes, RTL verification IP models come with C or C++ based APIs that already exist or already well tested. They're based on DPI coupling between the C model and the RTL transactor. And it's desirable to be able to leverage this IP into System Verilog UVM environments without having to rewrite it. So that's a good case for a hybrid test bench of reuse of legacy IP models. Interchangeable test bench heads. A single source piece of verification IP can get reused from multiple test bench methodologies. And I've got one slide that talks about that. And dual use drivers, we've got an example where you can take a UVM driver and you can equip it with a second TLM port, and so that in addition to pulling off transactions off of a sequencer port, it can pull out of this TLM port, which might come from another language. And I've got a slide that shows that. And finally, virtual platform test benches. We've seen a number of QEMU virtual platform derivatives out there which pair fast host-based virtual platforms with RTL designs under test. So we've got a diagram that talks about that.
So we've heard similar stories from several of you today and from our customers with a desire to interoperate your models with your test benches in different ways. Interoperability means agreeing on a common standard and also agreeing on an implementation. The simplest forms of interoperability involve plug and play rather than making a requirement on one side or the other. So we set out to achieve an independent, reusable, simple interoperability solution for System Verilog and SystemC. Something as simple as plugging an HDMI cable together. If both boxes agree on the protocol, then they don't need to be created in the same way as long as they have an independent agreed protocol. So we set out to create something similar, and we called it UVM Connect, as an enabling technology to leverage what we've got already with TLM. So UVM Connect will enable your TLM communication from SV to SC and back again, and it leverages the TLM 2.0 implementation, although also supports the UVM TLM1 and analysis ports. And it's a simple cross-language binding. The simplest way to make a binding is to have a string which is known on both sides. It's not rocket science, but it scales to most of the kind of complexities of test bench that we require to interoperate between the worlds of SystemC models and System Verilog UVM test benches. In addition, we have a command and control interface which lets your SystemC code control some aspects of the UVM test bench. We're not going to focus on that too much, but we're going to show you a couple of examples of the code, how we do the connection when SystemC is a slave or when the SystemC is a master. And just a note at the bottom there, as John said, this is a technology that we created in Mentor, but we intended from the outset to make it freely available. So it's been donated to Accelera for use and consideration by the working groups as appropriate. You can download the full tutorial from the website there and go into more detail on some of the code examples that I've got here.
So first of all, if we have this situation where we have some system Verilog code acting as producer and scoreboard, and some SystemC model which is consuming TLM transactions. On the system Verilog side, we bring in a package. We're already bringing in the UVM package. We bring in one additional package, UVM Connect. And then we have some system Verilog code to create our test bench, and the initial block is doing some connections. A very simple syntax, the UVMC TLM or UVMC TLM1, different variants of the connection depending on your situation. Giving those connections names foo and bar. And over here on the SystemC side, we're making the same connections. And you can see we've hash included a package, uvmc.h, and we have a namespace there. And that's all you need to get started with the UVM Connect. Package on one side, package on the other side, some very simple statements to build and start up. If the opposite situation is the case, system Verilog acting as a slave to SystemC. So over on the left-hand side, we have some SystemC code spawning producer, which has some threads, some background activity, and it's doing some API calls into the UVM Connect library, which lets it interact with the UVM world. In this case, we're showing some API calls that can control the UVM's objection mechanism and synchronize test bench activity. In this case, we've called our connection number 42, rather imaginatively. On system Verilog side, we just have one additional step when system Verilog is a slave, and that's to call the API UVMC_init. But apart from that, it's the same kind of connections, declaring predefined system Verilog objects to make the connection, and over on the SystemC side as well.
Here's an example of where we get some reuse out of some legacy APB transactor models. The green modules are DPI-based proxies for transactors running in RTL. Everything in the yellow is RTL, which can either run in your software simulator or on an emulator. It's using standard P1800 DPI coupling. And in the case of the master, we've encapsulated it as a TLM compliant target port. So basically, you've got a TLM2 initiator on the UVM side inside the driver, and you've got a TLM2 target on the SystemC wrapper. And effectively, you're using UVM to connect between those. So it's going to look something like this, where you've got your APB master driver class, which extends UVM driver, and it has a local initiator socket, which is just standard UVM. This comes with standard UVM. So you declare the socket, and it's pretty much a standard UVM driver class, but it's equipped with this TLM initiator port. So it's pulling things off the sequencer port because of the fact that it derives from UVM driver, and UVM driver has a built-in sequencer port. So it's pulling things off that and then pushing them through the initiator socket, which is UVM connected over to the SystemC side. And similarly, on the SystemC side, you've got a SystemC target, which is a standard SC module, and it also derives from TLM forward transport interface, which also makes it a standard TLM 2.0 target. Again, it's all part of the 1666 TLM standard. And then it has a B transport method, as all targets do. It can have a B transport method or in B transport FW if it's a non-blocking interface. Let's pick that apart in a little bit more detail. So if you look at the initiator, you've got sort of three aspects to it. You've got the construction, where you're basically constructing the socket over on the UVM driver. You've got the connection phase, where you're connecting, and this is where we make our UVM Connect call itself. So you can see right at the bottom there, it's a call called UVM Connect, and all you do is you give it two simple parameters. You give it your port object, and you give it your identifier. And if both sides give it the same identifier, the UVM Connect infrastructure rendezvous and connects them. And basically you have your connection. So it's as simple as making a connect call. And then finally you have your operation. The operation is your phase where you're in a little forever loop, and you're basically pulling sequence items off the sequencer port, and you're calling B transport on the initiator port and relaying them through the socket. So that's the operation of the master. On the target side, SystemC, again, you've got the construction phase. You're going to construct the driver. You've got a socket declaration. You do a standard TLM socket binding. And then on the connection phase, again, you got the UVM Connect. And again, two simple parameters, the port itself and a rendezvous identifier. And then for operation, you implement the B transport. So the result of calling B transport from the target, the initiator, results in B transport being called from the target. So that's a simple initiator target connection. We also support standard analysis broadcasters and subscribers, which are also part of the TLM2 standard, is a pattern where you have an analysis port and any number of subscribers to it. In this case, the subscriber is a standard monitor that's part of a UVC or an agent on the UVM test bench side. And that monitor, in turn, is itself a broadcaster to other subscribers downstream from it. So the monitor, in this case, acts as just a little relayer of monitored transactions. And the broadcaster is a TLM2 analysis port on the SystemC side, which has a DPI coupling to a monitor transactor. And whenever monitored records come in through the DPI interface, it broadcasts them out the analysis port. So again, I'm just going to quickly go through this. I won't take a lot of time, but it acts as a subscriber, but it's also a broadcaster to a downstream analysis port, which will then feed out to the UVM subscribers. And the SystemC one is a broadcaster with a DPI function that gets called whenever something comes from the transactor, and it in turn calls the local write method, which broadcasts it out to the analysis port. So again, just going through the phases, I'll just do it quickly. So there's the construction where we create an analysis port on the UVM side. There's the connection. Again, I'm using UVM Connect. Notice I'm using UVMC TLM1. So UVM Connect supports both TLM1 and TLM2 connections. Analysis exports are actually part of its TLM1 connections. And then initiators and targets are part of the TLM2 connections. So that's where I'm doing my connect. Basically, the operation is whenever the write gets called, it relays the write out through its analysis port, and that goes to all UVM subscribers. And then on the SystemC side, again, we constructed it. It derives from analysis port. So by deriving the SC module using multiple inheritance, also deriving from analysis port, it qualifies as a broadcaster. We connect it again, calling UVM Connect with the same very simple syntax. Give the handle of the port and then the name. And then finally, the operation is whenever its write gets called, it translates it to a generic payload transaction and propagates that down through its analysis port. So that's kind of the guts of how the code actually works. And I'll just show you some use case examples. I'll go over them real quick. So here's a case where effectively you're interchanging the test bench heads. What's shown in this green is actually that sort of dashed line is depicting the fact that there are implicit proxy ports within the UVM infrastructure that automatically get created. So they're hidden from the user. When you call UVM Connect, it will create those implicitly. You don't have to explicitly create ports for them. So it's basically just showing how you can have different types of test benches, but get complete reuse of the transactor model itself. We've also used it for dual use drivers. So here's a case where you've got a regular UVM test bench with a sequence, scoreboard, agent, everything, and it's getting all its transactions from that sequencer. It's not using its TLM2 port, but it is equipped with one. Now here's a case where I don't use the sequencer port, but I do use the TLM port, and I hook a SystemC test bench, and that SystemC test bench might be doing a front door, back door type of test where it's feeding front door transactions through that driver and getting reuse of the driver, and then doing backdoor accesses through a slave memory, which is also one of those TLM ports. So there's a case where you can have dual use UVM drivers to connect across the language boundary. Here's a case which is a virtual platform example where we took an ARM fast model virtual platform. We have an AXI agent, master and slave, both forming a bridge, and it's talking to some graphics subsystem. So it's using TLM connections, but we also hook onto it a coverage harness. So this coverage harness is actually SVUVM running in the same host simulator portion. So it's basically the SystemC itself is managing interactions to the virtual platform, but we're using the power of UVM for measuring coverage to tap off the transactions that come through the bridge and do some sort of coverage analysis on it. So there's an example of where you would then use UVM Connect because you're going across the SystemC UVM boundary. Here's another example. I'll just quickly go over it. It's an Ethernet packet router. It's got a mix of SystemC. It's using SystemC models, legacy models based on DPI for configuration handling of inbound Ethernet packets. It's using a system Verilog constraint solver to generate stimulus Ethernet packets. It's using a SystemC golden reference model of the same router. and it's using a System Verilog scoreboard and coverage analyzer. So again, everything crossing a dotted line boundary is effectively a UVM connection. And that's an example of a use of a hybrid test bench where you're sort of getting a mix of reuse of legacy models, but using UVM for some of the things that it's good for. So in summary, there's a good case to be made for hybrid test benches supporting legacy models, interchangeable test bench heads, dual use drivers, and hybrid test benches which combine the strengths of SystemC with those of System Verilog. And it's well supported through the standards combined with some open source packages, so there's really nothing vendor proprietary about this. It's completely standardized.